This example is for kinematics of a 6-hour robot with a spherical 3-axis wrist using the product of exponentials method. This robot here is a universal robot, and you can see it's got one joint here at the base that rotates around the vertical axis, and then joints 2 and 3 that stick out to the side, and then up here at the top we have a 3-axis wrist. So that rotates in 3 different directions. They're actually 3 separate joints and not a ball and socket, but for simplification, we're going to say that the joint centers are all at the same point. So the procedure for doing this problem. Step 1, we need to assign coordinate frames, omegas, and thetas. Step 2 is assign the initial points. And these will just be at the joint centers. Then step 3 is home configuration. Step 4 is the joint twists. So that is squiggle and squiggle hat for each joint. And then 5 finally is product of exponentials method, which is product of e to the squiggle hat theta for all of them times initial configuration. All right, we've got the base frame, which has the z-axis pointing up. And then this one is z6, point straight out. So these joints here, joint 1, joint 2, joint 3, this is joint 4, joint 5, joint 6. On the regular robot, J1, J2, J3, J4, J5, J6. Now that we have put in the z vectors, then we need to put in x and y. Well, it will be convenient if at least one of those can point in the same direction to find orientation between base and tip. So we'll say that x points out of the page. And then the y has to point perpendicular to that. Then the omegas, omega 1 points vertically because that comes from the first joint. Then omega 2 and 3, we'll say those point into the page along that axis. And so does omega 5. And then omega 4 points up, and omega 6 points in the z direction. And then finally, theta for each joint is just around the omega axis. Next, we'll find initial points. So for each of these, we can say, so they can be anywhere along the axis of that joint. So for simplicity, we'll say that P1 and 2 are here because that is, then they can both be the exact same thing because they're both along the z-axis for that joint. And then P3, and then P4, 5, 6, these all intersect here, so we'll call that P4, 5, 5, 6. That center. So now let's write down what each of those are. Okay, the omegas, omega 1 equals, that just points in world Z. Remember, all of these are going to be given relative to the base frame. So 0, 0, 1. That points up. Omega 4 also points up, so that's the same thing. And then omega 2, that points into the page, which is in the negative x direction. So we've got negative 1, 0, 0. And omega 3, omega 5 also do that. So we'll say that's also omega 3 and omega 5. So then the only one left is omega 6, which that points to the right, which happens to be the y direction. So 0, 1, 0. We can use this formula and get the omega hats. So for omegas 1 and 4, then those only have a component in the z direction. So that will be 0, 0, 0. And then in the z, we've got 1, negative 1, and then zeros everywhere else. Now for omega 2, 3, 5, those just have a component in the x direction. So zeros along the main diagonal. And we'll put a negative 1 in the x component. So that is here. Omega x is negative 1, and then the opposite of that would just be 1. Finally, omega 6 hat. This just has something in the y direction. So we'll have 0. And then the y's are at the corners, so that will just be 1, minus 1, fills zeros into the other locations. Now the p's, P1 and P2 are in the same location, which is L1 vertical and nothing to the sides. Remember, this is the initial configuration. So assuming that this position shown is the robot's initial configuration, we don't need to worry about angles that any of the joints have rotated. We'll just use L1, L2, and L3. So this is 0 in the x, 0 in the y, L1 in the z. And then P3. P3 is up at the same height, so we'll have L1 down here, but it includes a y component, L2, in the y direction. And then finally, P4, P5, and P6. That is, again, same height, so L1 in the z. And this time, it's even further in the y direction, so we'll have L2 plus L3, and then 0 in the x. So none of these have an x component. Then next we need to do home configuration. So T60 is going to be, we need initially, that'll be R60, triple zeros, O60, 1. Well, the rotation, if we look at this, to get from frame 0 to frame 6, then the x's point in the same direction, but y and z do not. Therefore, it must be a rotation around the x-axis. And it looks like the y and z's rotated 90 degrees clockwise. So we know that this must be a rotation around the x-axis. So we'll have a 1 here, and then 0, 0, 0, 0. Okay, so this should be cosine sine minus sine cosine. So then cosine of negative 90 is 0. And then sine of negative 90 is minus 1. The opposite of that is 1. So this is the rotation part. We fill in zeros along the bottom, 1 in the bottom right corner, and then we need the origin, which is the same as P6. So just 0, L2 plus L3, L1. Now we need to get the twists. Since these are all revolute joints, then we'll use the same formula to get the twist coordinates for each one. Negative omega cross P and omega. So those are all going to be 6x1 vectors for the twist coordinate, squiggle I. So we will just put that all in a table. So we'll have the joint 1, 2, 3, 4, 5, 6. And then we'll have this first part, negative omega cross P, and then omega. So for each of these, we can already fill out the omega. It is from what we got up here. So omega 1 and omega 4 are just 0, 0, 1. And then omega 2, 3, and 5 are negative 1, 0, 0. And then omega 6 is just 0, 1, 0. So then for the top parts of these, we need to do the cross product. So if we do negative omega cross P for each joint, then for the first one, we have 0, 0, 1 crossed with 0, 0, L1. Well, that is going to be a Z cross a Z, which ends up being 0. So this will just be 0, 0, 0. And then kind of our basic formula for this cross product, we'll say I, J, K, omega X, omega Y, omega Z, PX, PY, PZ. We'll use this basic formula for the cross product. So then for each of those, we'll have I, J, K. And then for joint 2, we've got negative 1, 0, 0. And then P2 is just 0, 0, L1. Okay, so if we do the cross product for joint 2, then in the I component, we have 0 minus 0. Then in the J component, we'll have, let's see, negative L1 minus 0. And then in the K direction, we'll have 0, 0. So then we'll write that in over here, 0 minus L1, 0. And then for joint 3, omega 3 is the same, but P3 is not. So that will look a little bit different because we'll have an L2 here instead. So for joint 3, this will be 0 minus L1, L2. So we just put that in over here, 0 minus L1, L2. And then for joint 5, really similar, but this is instead L2 plus L3. So that will be 0, negative L1, L2 plus L3 transpose. So we just put that in right here, 0 minus L1, L2 plus L3. Now omegas for 4 and 6 point in different directions. So if we do omega 4, cross with P4, so for joint 4, we need I, J, K, and then omega 4, we said points in the Z direction, 0, 0, 1. And then P4, we get from here is 0, L2 plus L3, L1. So that comes out to be in I hat, we have 0 minus L2 plus L3. But then this also is a minus, so those cancel. And then in the J direction, we have 0 minus 0. And then the K direction, 0 and 0. So we'll plug that in. L2 plus L3, 0, 0. And then finally, joint 6. I, J, K, and omega 6 points in the Y direction, 0, 1, 0. And P6 is the same as P4, which is 0, L2 plus L3, L1. So if we do the negative and do that cross product, then we get in the I direction, negative L1, and then in the J direction, 0 minus 0, then in the K direction, again, 0. So we just fill this in, negative L1, 0, 0. So these are the twist coordinates. And then finally, to get the twist, we just use this formula. So we would take the omega hat, which we got for all of these, and put that in the R component, and then we'll take the negative omega cross P, which is all this stuff, and put that in the position spot. And then we just have all zeros in the bottom. Then finally, to get T6 0 of theta, then we just multiply all of those together. We need to get e to the squiggle hat 1, theta 1, times e to the squiggle hat 2, theta 2, e to the squiggle hat 3, theta 3, e squiggle hat 4, theta 4, e squiggle hat 5, theta 5, e squiggle hat 6, theta 6, finally times t 6, 0 of 0. So this is the final answer. Now that we've found all of these things, we could program this. But in order to get this matrix exponentials, then there's another formula we need to use. So we can use Rodriguez's formula here at the top to get the e to the omega hat theta for each of the joints. Put that in the rotation spot, and then to get the position part, we just use the second half of this formula, and then we get the matrix exponential. So this is Rodriguez's formula, and this is the matrix exponential. Now this last part, omega transpose V0, because there's no translation, then that part goes to 0. So it's a little bit simpler to calculate. So then finally, once you calculate all of those things, then you chain them all together and multiply by the home configuration, and that gives you the joint transformation, or transformation from base to end effector as a function of time. Here is a MATLAB simulation to help with visualizing a robot. You can see here, this is going to simulate each joint. So each joint will go from 0 to 30 degrees consecutively. Now for the actual math part, you can see that I use exactly the same procedure that we defined for solving the problem by hand. So defining link lengths, joint origins, velocities, twists, zero configurations, so on and so forth, and then calculating the robot for every point during the trajectory. Then finally, to plot. So let's run it.